Okay, our next topic is capacitance. Capacitors are used to store charge and electrical energy, and a capacitor is fairly simple. It's just two sheets of metal that are hooked up parallel to each other. Now, if you connect it up to a cell and close the switch, then there is an open circuit here. So you wouldn't think that any charge could flow, but remember that these things are rather think of these things as being large reservoirs. And so what will happen is that when you close that switch, here there's excess charge at the negative terminal of the power supply. So there's excess negative charge here. And so what will happen is some of those negative charges will push on the negative charges that are already in the wire, and these negative charges will move a little bit, and they'll start to pile up on this plate of metal. Now, the plate of metal actually has quite a bit of room, if you like, to store excess negative charges. As that's happening, negative charges are going to leave this upper plate just because they're repelled by the excess negative building up here, which is going to leave excess positives or a lack of negatives on this plate. So as it says, charge spreads out from the terminals of the cell to the plates due to the repulsion of like charges. Now, in all of this, there's nothing flowing through the gap. There's just charge arriving on this plate and charge leaving that plate. Now, eventually, of course, that charge flow will stop because what'll happen is that as the minuses build up here, they'll start to develop some repulsion due to all these minuses. So these minuses will stop the minuses in the wire from flowing. So there's a push from the cell, but you'll build up a push here from this plate that will eventually stop all flow. So the key thing is that charge flows from the terminal of the cell to these large plates which act like reservoirs, but then none flows through the gap. So when you build up enough minus charge on this plate, and when you've pushed enough minus charge away from this one, then the flow will stop. And we say that this capacitor is now charged. Now, how long that takes, as we'll see later, depends on how much capacity these metal plates have, and also how much resistance there is in the circuit. But typically, it doesn't take very long to happen. Now, we're going to define capacitance then as the amount of charge stored for a given voltage. So it's a ratio then. It's charge stored for a given voltage. And the units then will be coulombs per volt. And a coulomb per volt is called a farad, named after Michael Faraday. Okay, so that's our definition of capacitance then. So the reason it's a ratio is just that you'll store a certain amount of charge at 10 volts on a 5 microfarad capacitor. But if you increase the voltage, because there's extra stored energy here, there'll be extra repulsion, you'll actually store more charge on the same 5 microfarad capacitor. In fact, you'll store twice as much. So doubling the voltage, you'll get double the charge. So let's try and draw that in our picture here. And now let's just calculate, based on the definition of capacitance, the charge stored in each case. Because capacitance is charge stored for a given voltage, we just cross multiply and get charge is capacitance times voltage. So here we've got a 5 microfarad capacitor connected to or charged up to 10 volts. Now that micro, we can just keep it around, and it actually ends up being a convenient way to answer this question. 5 times 10 is 50. Then you get micro, and you've got a farad times a volt. Well, based on our definition of farad, a farad times a volt is a coulomb. So this is just 50 microcoulombs of charge. Now, if we increase the voltage, then there's more repulsion here. We're going to push more charge on the plate. But the 5 microfarad capacitor will still store the same amount, or proportionally, the proportion of charge to voltage will be the same. So you'll get more double the charge having hooked up double the voltage. That's what I was trying to say. So here with our 5 microfarad capacitor at 20 volts, we've now got 100 microfarad times volt is Coulomb. But the ratio is the same. So capacitance is charge stored for a given voltage. Now, for the energy that's stored, because capacitors store both charge and energy, we recognize that the capacitor initially discharged has no stored energy and no stored charge, and then we build up to a voltage V and a charge Q. So the energy isn't just going to be the product of charge and voltage, because while the charge is building up, the voltage actually isn't constant. The voltage is building up too. So we could write it as adding up a little bit of charge, arriving on some plates which are at voltage V, where that voltage is not constant. What will that voltage be? Well, we could write that voltage. Remember, if capacitance is charge stored for a given voltage, that means voltage is charge stored per capacitance. So this Q variable is building up, but the capacitance C is, of course, a constant. So we get the integral of Q dQ, which, of course, is Q squared over 2. So Q squared over 2C. Now, using our capacitance definition, there's a couple of equivalent forms that we can turn this into. We can write it as, and this is the way it's usually written, by substituting in for Q, put it in as CV, be C squared V squared, cancel off the C, you get 1/2 CV squared. So that's the energy stored in the capacitor. Another substitution you can do is you can substitute for capacitance, Q over V, and then you get QV over 2, which another way of thinking about it is it's the product of voltage and the average charge. So if you don't like the integration solution, perhaps this one appeals to you more. So we've got thus a definition of capacitance, charge stored for a given voltage, and an expression for the energy stored in a capacitor. Now, another idea is that of a dielectric. Up until now, we've just been saying, okay, we've got these two metal plates that just act like reservoirs for charge, and charge can build up there. But capacitors often actually have something in between the metal plates that's called a dielectric. And this dielectric enables the capacitor to store more charge. Why? Well, the dielectric itself doesn't conduct. The dielectric is typically a non-polar covalent compound. But even if it doesn't have free electrons and doesn't conduct, if this plate starts to build up negative charge and this plate positive charge, you will polarize the molecules in the dielectric. That means that the electron clouds in the dielectric molecule will move a little bit to this side and leave the other part of the dielectric molecule a little bit positive. So this shifting of the electron clouds, what it really does is you've now got essentially a little bit more positive charge down here than you had before. Now remember, the charge flow in the wire stopped because of the electric repulsion from these negative charges on the plate. But now putting these positive charges there, you've essentially are shielding or reducing the effect of this negative charge. And as a result, you actually now build up more negative charge on this plate. You could say there's extra negative charges that are pulled onto the plate by the plus end of the dielectric molecules. That's what it says here. The plus end of the dielectric molecules attract more negative charges onto the negative plate. So with a dielectric, you store more charge. The other thing that's true about a dielectric is our electric field, we know, would go away from plus and towards minus. So that's the electric field due to these free charges on the metal plate surface. You actually have a little dielectric electric field here too, which is away from positive and towards negative. And you could see that that little bound charge, as it's called, bound because these aren't free, that bound charge electric field reduces the free charge electric field. So the dielectric also reduces the electric field. So it does a couple of things. By polarizing, the dielectric enables us to store more charge. By polarizing, it also reduces the electric field inside the capacitor. Now this is represented by a dielectric constant, and this just is the factor of increase for the stored charge. So if you had a dielectric constant of about 5, that just means your capacitor can store 5 times more charge than it did before. So this is a Greek letter kappa, and it is a multiplicative factor of capacitance. So this is the capacitance when there's air, no dielectric. This is the capacitance with the dielectric. We could add one more thing here. We could say that if E is the electric field, and let's spell that properly, F-I-E-L-D, and that'll be in newtons per coulomb, and capacitance is in farads, and dielectric constant has no units, it's dimensionless. Then we say the electric field is actually reduced by the presence of the dielectric. That's the letter kappa right there. So this is the electric field with no dielectric. This is the electric field with a dielectric. Okay, now, so we've just said that when you put your dielectric in here, then there's a bunch of positive charges here that actually pull more charge onto this lower negative plate, allow you to store more. The same thing is true if the capacitor has a smaller plate separation. Let's say you've got this capacitor here, and let's say, and this is a common piece of lab apparatus, that you're able to actually move this plate in towards the negative plate. What you'll find is that more charge will be pulled onto this negative plate because these positive charges are now closer than they were before. So they're going to exert an attractive force and pull more charge on there. The positive plate attracts more negative charge onto the negative plate if we bring the capacitor closer together. So with a smaller plate separation, let's call that distance d, okay? With smaller d, you get more charge. But capacitance is charge stored for a given voltage. We haven't changed the voltage, we've just changed the Q. So with more Q, the capacitance is also larger. So that tells us that there's inverse variation between plate separation and capacitance. Because when we made the plate separation smaller, we store more charge, we get a larger capacitance. The capacitance also depends on the area of these plates, because a larger plate area means you've got a larger reservoir for storing charge. Finally, you do the experiment and you get the slope, and the slope turns out to be a really small number, and so we give it a symbol. It's a Greek letter epsilon with a subscript 0, and you can call that epsilon 0 or epsilon naught. And it's a really tiny number just because the charges that you store on capacitors are typically fairly small. Now, we did refer to epsilon naught earlier when we were talking about Gauss's law, and remember that it's 1 over 4 pi times k, where the k is 9 times 10 to the 9. So we could have expressed Gauss's law in terms of epsilon naught or k. Here, really, for capacitance, it's much easier to finally use the proper physical constant epsilon naught. And, well, let's put a box around that one, because that's the capacitance of a parallel plate capacitor. Simplest geometry. And so, to that, we've got the definition of capacitance in general, charge stored for a given voltage, and the energy stored in a capacitor, and lastly, the effect of a dielectric. It's time for a quick example then. Here we've got a parallel plate capacitor. There are the dimensions of the plates and the plate separation. It's got an air dielectric to start, and it's connected up to a 50-volt cell. So we can visualize that then. Here are the capacitor plates. They are 20 centimeters, 0.2 meters by 30 centimeters, 0.3. That's the upper plate. There's a lower plate here parallel to it. And these two plates are hooked up to a cell. and it's a 50-volt cell. So remember, charge will spill from the cell onto these large metal plates. None will flow through the gap. The capacitor will charge up until it reaches 50 volts. What is the capacitance? Well, we just said it depends on the area of the plates directly and the plate separation inversely. So we put in our 8.85 times 10 to the negative 12. And what are the units of epsilon naught again? Farads per meter. Our area is 0.3 meters by 0.2 meters. And then our plate separation, 0.5 millimeters. That's 0.5 times 10 to the power negative 3 meters. So if you work all this out, you get still 10 to the minus 12. Meters, meters, meters all cancels, so it's farads. It's 10 to the minus 12, by the way. And then it is 1.06. Now, 10 to the minus 12 as a metric prefix is a pico. And a picofarad is a pretty standard capacitor. So even for fairly large plates, 20 centimeters by 30 centimeters, fairly close together, half a millimeter, you really don't store a whole lot of charge. What's the electric field? Well, the electric field is just voltage over plate separation. So that's 50 volts over 0.5 millimeters. That works out to be 10 to the power 5 newtons per coulomb. How much charge is stored? Well, capacitance is charge stored for a given voltage. So charge is capacitance times voltage. You got 1.06 picofarads, and you're charging this up to 50 volts. So you get 50 times 1.06, 53 picocoulombs of charge stored. What's the energy? Energy stored in a capacitor is 1/2 CV squared. Here, in order to get it to work out to be joules, we have to, well, we can use pico because we're not squaring it, but the voltage, we've got to use 50. We can't use any engineering metric prefixes there. So 50 squared times 1.06 picofarads. Actually, sorry, it's easier instead of doing pico here, just because we end up bumping up a power of 10. Well, I guess it's not the end of the world. Sorry, I'll stick with my original plan. You'll just have to bear with the metric prefixes a little bit. So it ends up being 13. Let's see, I better pause and work this out properly. Yeah, no, I was right. So it's 1325, and then it's picofarad volt squared. A farad volt squared is a joule, but 1325 picojoules is 1.325 nanojoules. Okay, so what are we asked for here next? How would each of these quantities change if we stuck a dielectric in the plates? So the dielectric will increase the capacitance by a factor of, let's see, capacitor voltage. Oh, sorry, I missed that. That's 50 volts. The capacitor charges up to 50. And then this is E, and now F says, what happens if we put the dielectric in there? Well, the capacitance will be greater by a factor of 1.5. So it's 1.5 times the 1.06 picofarads. The electric field gets smaller. So it was 100,000 or 10 to the 5. It's going to be smaller by a factor of 1.5. Because the capacitance is larger by 1.5, so will the stored charge. And then so will the energy be larger by a factor of 1.5. The 50 volts doesn't change, but because the capacitance gets larger, so does the stored energy. Okay, so where was I? So the charge ends up being 1.5 times bigger, and the potential energy also ends up being nanojoules, 1.5 times bigger. And that concludes our introduction to capacitance.